Try to get through here today. I want to talk about this extra chain rule topic having to do with taking the derivative of inverse functions. And then I want to talk about implicit differentiation, which is another like chain rule related topic. Okay? So if we go back to like our Algebra 1 or pre-calc class, when we talk about inverse functions, what's the algebraic definition if two functions are inverses?
I know this one, I swear.
They have
Like they equal the same thing when flipped around. If that makes sense. Right? Yeah, like G of f of x would equal the same thing, right?
It's their composition gives you x.
Oh, that's it?
That like one function cancels the other function out. Right? This is the wrong hour. I think he's in third hour.
Okay.
We're in second. So what else does this imply? This would say that if f of a is equal to b, then what can we say about g? That g of b has to equal a, right? When we make an inverse, we're basically transposing the x and y coordinates. So these are the two big pieces that we need for what we're about to do. Okay? So let's say we have f and g that are inverses. So we can say this. If I take the derivative with respect to x of both sides, what is the derivative of f of g of x?
f prime g of x times g prime of x.
Yes, excellent. It's just the chain rule, right? That's literally the definition for the chain rule. And the derivative of x is 1. So if I divide both sides by f prime of g of x, if f and g are inverses, the derivative of g should be 1 over the derivative of f composed g. Right? That's all we're saying. All right. So this is the other formula that we'll use frequently. I often never think about this as a formula. I just think about doing the chain rule at that step. But whatever way you want to think about it is fine. Let's look at some examples here. I wonder, did I clip this? Yeah. I'm going to try to make that a little bigger. I know, those of you in the back that are all the people with the worst eyes. So this says the functions f and g are differentiable. For all x, f of g of x is equal to x, and g of f of x is equal to x. If f of 3 is 8, and f prime of 3 is 9, what are the values of g of 8 and g prime of 8? So g of 8 we can do really easily, right? What's g of 8 going to have to be? 3, right? Because if f of 3 is equal to 8, g of 8 has to be equal to 3, since they're inverses. Does that feel okay? Okay. G prime of 8 then is going to be 1 over f prime of g of 8, right? So what's g of 8 equal? 3. And what's f prime of 3? So we're done.
Oh.
So far, so good? Again, these problems typically aren't terribly difficult, but if we haven't talked about like what an inverse is and like you use the chain rule when you do the, like, you're clueless as to what to do if you haven't really thought about this before. And some of these problems can be trickier than others. That's like the simplest version that we saw right there. But that was pretty easy, right? Carmen.
How did you get f prime 3 from?
So g of 8 is equal to 3, right? And then f prime of, I'm sorry, and then f prime of 3 is just 9. So that's, does that feel good?
Yes.
Okay. All right, so the next example here, it says let f be the function defined by f of x equals x squared plus x, and g of x equal f inverse of x, and g of 2 is equal to 1. What is the value of g prime of 2? So we know right away we know that, right? Since f and g are inverses, which is just, this is just another way of stating that, right? So that's going to be f prime of 1. And I can calculate f prime because I've told what the function for f is. And I'm 1/4. Everybody's okay there? Again, pretty much the same idea as the previous problem. The only difference here was I actually had to figure out what the derivative of f of 1 was going to equal. I wasn't just given it to me in the problem. I had to take the derivative of f and then plug the 1 into it. Elena, what's up? You're making faces.
Can we go over that?
Sure. Because I know that g of 2 is 1.
I
Emma. Yes, exactly right. Because we know f is this, so its derivative has to be just a power rule derivative, easy, no big deal. And then we just plug the 1 in. Everybody feeling good so far? Again, not tricky, but like, if we haven't talked about it, it sure is, right? Let's go and do some more. So again, we're going to notice that like each one of these is like maybe a little bit trickier than the one before. It says here that let f and g be functions that are differentiable everywhere. If g is the inverse of f and g of -2 is 5, f prime of 5 is -1/2, then g prime of -2 is equal to what? So because f and g are inverses, right away I can write this. Everybody agree? Do we know what g of -2 is? Okay, so let's replace that. And do we know what f prime of 5 is? So 1 over negative 1/2 is negative 2. And we're done. Got
I feel like that.
well, the book doesn't have any problems that match up like this. There are a bunch in the practice, my EP practice, that I'm going to build for the review at the end, for part of your multiple choice review. That'll have a bunch of these in here. What?
Are those ones like harder?
They're on par with these.
Okay.
Again, I don't think that, like, I think this is the hardest one.
Okay. Oh.
So h of x is equal to f compose g of x, then h prime of 1. Notice we don't have an inverse relationship here, right? But what can we say? We have to do a chain rule when we differentiate both sides, right? Yes, those are, well, no, they're all, it's f of 1, g of 1, f prime of 1, g prime of 1, f of 2, g prime, or f prime of 2, g prime of 2. So they're all just normals or first derivatives, but the first derivatives you have of 1 and of 2. So if we wanted to do h prime of 1, we'd say that, right? And what is g of 1? 2. And what's g prime of 1? Negative 3. And then what is f prime of 2? Right? So again, yeah, right? But again, like if you haven't seen them, it's like a chain rule example and not like one that we kind of see. I think that was my last example I had pulled. Does that feel okay, Emma? Yeah, so this was me doing the chain rule, differentiating that. Right, so just derivative of the outside times derivative of the inside. You guys feel okay on this? I'm sure when you look at more my EP questions, maybe you'll run into one that was trickier than the ones I pulled, but I think they're all fairly similar in that regard. You just have to be a little bit careful with like what stuff you need. Elena? Okay, so here's what I would tell you. In general, if you're getting errors, when you do this, do you get like a bunch of errors underneath?
Yeah.
Okay, so here's what you should do. Right click on the notebook that's giving you the errors. Hit close notebook. Yep. If it says it's syncing, hit cancel. If it gives you an error, say okay. And then go down to, after it's closed, go down to more notebooks, and then just reopen it. And then push another sync. And usually that'll clear all those errors that you're getting and get things moving again for you. Yeah, it'll take a minute, and the sync will take a long time if it's been having errors for a while, because now it has to check every single thing. So the sync could take a minute, but you'll start, if you're in the content library and stuff is missing that should be there, you'll see it start popping in as that sync is going. Is that?
Oh, it's there.
Yeah, good. Good.
Thank you.
9 out of 10 times that'll take care of whatever's ailing you.
Okay, so you can-
All right. So let's talk about implicit differentiation here. So what about, or what should we do if we're trying to take the derivative of an equation without a obvious independent dependent variable relationship, right? Where it doesn't start y equals or f of x equals, right? What if it's something that looks like x squared plus y squared equals 25? What if there's sine of y plus e to the y plus,
Inverse of sine.
well, you can't, how are you going to get the y's in one place, though? If you have y's in two different places, you're not going to be able to get y by itself, even in some of those cases. This one, I guess you could, but let's not do it that way because it's actually easier to do what we're about to do. Nope. We're going to use what's called implicit differentiation. Okay. So, oops. I thought I had it. We're going to find out right now together. So, let's say we have x squared plus y squared equals 25. We're just going to start by doing the derivative of both sides. So far, so good? Okay. Now, if I want to do the derivative of x squared plus y squared, I can think about that as the derivative of each piece, right? What's the derivative of x squared? Okay. What's the derivative of y squared? Okay. And what's the derivative of 25? Where's the dy dx?
Wait, what? It's gone.
Well, it says find dy dx.
Well, we took the derivative, so it's gone.
So technically here, what we've done, we need to use the chain rule. When I do the derivative of x with respect to x, I get technically like a dx over dx. And that's just 1. When I take the derivative of y with respect to x, that creates a dy dx. That I need it to still be there, because that's now what I need to get by itself. So whenever I differentiate with respect to another variable, if I'm differentiating y's with respect to x's, I get a dy dx. If I'm differentiating t with respect to y, I get a dt dy, right? Whenever the variable that I'm differentiating doesn't match the way that we're taking the derivative, or the variable, whenever the variable that I'm differentiating with respect to does not match the kind of variable that I'm differentiating, I get a d something of some, something, right? Hi, Tessa.
Yeah.
So, to solve this for dy dx, what do we need to do then? Subtract 2x from both sides, and then divide by 2y, right?
Oh.
Just doing like basic algebra 1 algebra, right?
Wait, what?
Oh, God.
So we wanted to find dy dx, right? So I'm just getting the dy dx by itself. So I subtract 2x from both sides, and then divide by 2y,
Oh,
I see.
like we're doing some like algebra 1 algebra, right?
Yeah.
And then I reduce the fraction, and I'm left with negative x over y.
but then what's on the other side?
The DYDX.
Yeah, so I have dy dx equals
Oh,
negative
x over y, right?
Back to finding like what's DYDX. How do you know like when you're like P in respect to Y? How do you know? Is it always Y?
The direction tells you we're differentiating with respect to x,
Oh, because it tells. Oh, because it'll tell you. Okay.
right? So if it asks for dx dy, we would be differentiating with respect to y. So when we did the derivative of x, we'd get a dx dy. And when we differentiate y, we get dy over dy, which is 1.
so the numerator basically tells you which one to solve for.
Yes, I guess. I would think the other way around. The denominator tells you what variable you're differentiating with respect to, but yes. That's okay. It means essentially, I think we're saying the same thing. So that's part A. Part B says, find the equation of the tangent to the circle, yada, 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 at the point 3, 4. To write the equation for a tangent line, what do we need?
The slope.
Point and a slope, right? Do we have the point?
Yeah.
Yep. So all we need is the slope. How are we going to get the slope? My slope should be dy dx evaluated at the point 3, 4, right?
Wait, is that line?
Yeah.
That's just up straight down.
Yep. So my x is 3, and my y is 4. So there's my slope, because I have a negative sign,
Oh, sorry.
right? So we can just write y minus y1 equals m times x minus x1. And if you want to rearrange, then, oh, sorry, it should be a 3. Thank you. Want to rearrange that to be slope-intercept, you can, but you don't have to.
Oh, okay. So,
Emma,
so after the negative 3 and 4, is that's just the x over y? Like you just plug it into that.
I just plugged it in the 3 and 4 into the equation for dy dx. Correct.
What if
I did the point slope formula, y minus y1 equals m times x minus x1. Because I had a point and a slope. You could do slope intercept if you prefer and then solve for b and then rewrite it. I don't like doing that. Feels like extra steps. I can just plug in and I just have an equation. All right. Oops. All right. So next example. Shh. It says find y prime if x cubed plus y cubed equals 6xy. Okay, y prime is the same as derivative of y or dy dx, right?
Yeah.
Everybody's okay with that notation? I'm going to always use the dy dx notation. I think it's just a little bit clearer, at least initially. Okay, so let's go ahead and take the derivative of both sides. Derivative of x cubed is 3x squared. The derivative of y cubed is 3y squared.
Uh,
3y squared.
dy.
There you go.
Oh, I was like,
There you go. How do I do the derivative of 6xy?
3. I mean 6.
Nope.
6y.
What? Yes! That's a product rule. X times y. Those are both variables. They're separate functions. That requires a product rule. So 6x times the derivative of y should be 1 dy dx. And then 6y times the derivative of x should be 1.
No, this makes sense. This one's good. I like this.
Yeah, this one's making sense so far.
Good.
So funny though.
So
I don't know.
what I did the product rule. So I did like the derivative of x times y. So I did x times the derivative of y plus x or plus y times the derivative of x, and then I distributed the 6 through.
Oh, so
There's nothing that we flipped.
No, like
That's what Elena's doing in her head, and that's fine, but there's no flipping that happened. It's okay to say that, though.
Yeah, it's like the dy notation goes to the x, and then the dx to put 5. I know it's
In your head, that makes sense. That made no sense to anybody else. I know what you're saying, but let's not think about it that way.
Yeah.
Elena, if it works for you, I'm glad.
Okay.
So to get dy dx by itself now, I'm going to move the 6xy dy dx to the other side by subtracting it. And I move the 3x squared to the other side by subtracting it. Now that the dy dx's are on the same side, I'm going to factor that out like a greatest common factor. So far, so good. And then to get the dy dx alone, I'm going to divide by 3y squared minus 6x.
Yeah.
Which I notice can reduce, right? I'm sorry, what?
Why do we want the x's together with y's?
Because we want to get the dy dx by itself,
Oh.
right? It wants find y prime, that's dy dx. So that's the thing I'm trying to get by itself. Oh, thank you, 2x. Good. Isabel. What, who? She was saying that, look, oh, the dy dx went with the x and the dx over dx went with the y. That's all she was trying to say, which is like a silly way of thinking about it, but that's like, okay, that's fine. It only did that, it only did that because it was x times y.
But they do that because the y prime was 1.
Yes.
So it's y prime that's the 1, and it's just going next to the y prime.
Kind of, yeah.
Okay.
Will it be like that every time?
No,
Oh.
that's why it's a silly way of thinking about it, but that's okay.
Because the y-axis.
If it was 6xy squared, you'd have 12xy dy dx, and there would be a dy dx and a y still, right? And you'd have y squared, or 6y squared is the other thing, right?
Can you write out like a samples on the side?
No, because it's like we're like chasing something that doesn't need to be chased right now. Like we're obsessed over something that like somebody said as a comment that I'm like, it's like, okay, that's fine, but don't think about it that way. And you're like, no, I really need to think about it that way. When I just told you, I was like, I don't want you to think about it that
Not
way.
like her way, but like the original way, because I know that it isn't required.
Oh my goodness, all we did was this. We did the product rule,
So that,
right? I just did the, I did 6x times the derivative of y plus 6y times the derivative of x. That's all we did. I just wrote down, because the derivative of y and derivative of x were really easy derivatives to do, I just did them in my head. Is that okay? Okay. All right. Part B then asks to find the derivative of some tangent to the curve at the point 3, 3. We have the point. What else do we need to write the tangent line? The slope. How do I find that slope? Yeah. I use dy dx and I plug in 3 for x and 3 for y.
Oh, it's just chill.
So 6 minus 9 is negative 3. 9 minus 6 is positive 3. So my slope is negative 1.
Whoa, what happened?
Everybody's okay there? Okay. Yep, I just plugged 3 in for x and 3 in for y to get my slope, and then I wrote my slope-intercept equation. Part B says, at what point in the first quadrant is the tangent line horizontal? What are we going to do with that? When the slope is 0. Very good. So our derivative, 2y minus x squared over y squared minus 2x has to equal 0, right? So when is a fraction equal to 0? When the numerator is equal to 0.
Yeah.
Everybody's okay there? Okay. And if we add x squared to both sides, we'd have this, right? So we'd say that x is equal to plus or minus root 2y when we square root both sides. Everybody's okay there? But if we want this to be in the first quadrant, what can we say?
Plus.
Has to be plus, not plus or minus, right? The x-coordinate must be positive. And when we take the square root of something, what kind of number has to come out?
Rational?
A positive number, right? You can't take the square root and get a negative.
Yes. Yeah, we're basically, yeah.
Is that okay?
Yes.
So my point then would be the point x comma square root 2y. And I think that's probably the best we can do with that. Let me double check something.
If your x is equal to the square root of 2y, then your x is equal to yeah, that's a good question. That's a great question. Oh, dude, thank you.
let's do this.
Yeah, what if,
Yep, because I haven't, this is not what I want. I want this. I do want that though.
now you plug it in for X.
Right, because we have to go back to our original equation. And now that I'm looking at this, I don't like this. What if we said instead that y has to just equal 1/2 x squared?
Okay.
I like that a little better, right?
Yeah. Yeah.
Because I don't really want to I don't want to have to cube the square root of 2y. That stinks. But I don't mind cubing 1/2 x squared, right? That's a little bit nicer to me. Oops. Oops, equals. So if I move this all into the same side, and now I can factor, so I can factor out an x cubed. Right? So applying the zero product property, I have x equals 0. And if x equals 0, what does y have to equal then? If I go back to this equation, if I plug 0 in for x, y is 0. Is that okay though?
No.
Why not?
I don't know. I just have a feeling.
If x and y are 0, is my derivative still have slope 0? No. So I had to check for an extraneous solution there.
Oh.
So that one didn't count.
Because it's young.
No, why was y 0?
Because if you plug it back into the x cubed, it's like
Oh, true.
Right?
Okay.
So now I do this one. So add 2 over, that's 2, and then I multiply by 8. So that's 16. So the cube root of 16 looks good, right? The y then is going to be what? It's going to be 16 plus y cubed equals 6x, oops, not x, 6 cube root 16 times y. Yuckarooskies.
What's going on? You like divide the y? No, what do you even do?
That's the key to do with
What would I do here? That's a great question. All right, let's think here.
What did they do?
what's not gonna do it.
Well, dividing by y is bad because you have a 16 still. So here's what I would tell you. This is, not no solution, but it's not going to be solvable by hand. What can I do? Use my calculator to graph it and find an intersection. Absolutely right. Or in this case, to find a like an x-intercept. Well, I'm just going to replace the y's with x's
Oh, yeah, but.
and just solve for x.
Oh, I wrote this thing wrong.
Come on, calculator. You're supposed to show
Oh,
up.
never mind, I forgot.
So this is what I would do. I'll do x cubed minus 6, and then we'll do well, let's write it this way, times 16 to the 1/3 times x plus 16. And then we're going, what? Oh. I'm going to do zoom standard. Look at my graph here. So I'm looking for where it's crossing the x-axis over here. So I have two places, right? Because it says that we're only looking for quadrant 1. So I know the x and y's, the x's have to be positive, or the y's have to be positive. So I'm only concerned about these two values.
Wait, it said only in quadrant 1 in the problem.
Mm-hmm.
Oh, okay.
And we're looking for zeros. So the left bound, I'm going to just move my cursor so it's somewhere to the left of the 0. Move it over to where it's right of the 0. Press enter. So 1162. I know. It's hard, guys. And then we'll do the same thing, left bound, right bound, guess. So 370 or 175.
Or you can plug it back in to find it.
We have x and y's, right?
So that's
We're done. Yeah.
Did it just ask for the points?
Now we're done.
Okay. So would we ever have a problem where we have to go to graphing, basically?
You might, to do the solving, if the polynomial's not going to be solvable by hand.
Yeah. At what point should you just say, like, this is solvable by hand?
Whenever you feel like it.
Okay, cool. I like that.
Mhm.
So pretty much just like as soon as we get like an equation, you can just graph it.
Sure.
Alright, cool.
As long as you get it down to one variable or whatever. All right. Let's do another example here. So here we have sine of x plus y equals y squared cosine x. Again, we want dy dx. So when I do the derivative of sine x plus y, how do I do that?
Like,
Chain rule. Good. So what's the outer function? And the derivative of that is? So derivative of the outside, inside stays the same. And what's the derivative of x plus y?
Okay,
1 plus 1 times dy over dx. So I'm just going to write dy dx. Yeah.
hypothetically, what happens if you like distribute it? Like if you distributed the side?
It's massively wrong.
wait, so where you wrote dy dx is the same thing as saying it's type 1.
Why 5?
Well, what's 1 times anything?
Well, yeah, I know. I just wanted to make sure.
Yep. So to do the derivative of y squared cosine x, how do I do that? Read a what? Product rule.
let's see.
Well, you just take the derivative. That's the product. It's the product.
I am doing the derivative of y, right there.
Okay, wait,
So that's
five,
five.
so it's five, so at, it's a y squared.
It's just one function times the derivative of the other plus the other function times the derivative of the other, right? Like it doesn't, f's and g's, like don't make it harder on yourself.
Why, I think prime cos x, second. Like, isn't that just doubling it, like, are we that same exact thing?
What?
How is that like the product?
Yeah,
Because
maybe him confused.
this y, isn't this first one the same? That makes sense to it different, but why wouldn't we just make the cos x in the first one, like sine x?
He's gonna do that.
I'm going to.
He's about to.
Oh.
I'm just writing my work because last time I did it quickly in my head, everyone was like super confused at what I did, and I had to write it this way anyway. So I just figured I'm just gonna keep showing my work. So the derivative of cos x is negative sine x, as Elena has pointed out to us. And then the derivative of y squared is
2y dy over the
excellent.
Dude, I'm on fire right now.
Since we have to,
Shit, anytime you do the derivative of y,
I'm getting there.
it's the derivative with respect to x, so it has to be dy over dx.
It's supposed to be a y next to the d.
Yeah, everything.
No, it's like dy dx times, or dy dx y squared.
Right.
It says d over dx, it's supposed to be y
So
there.
when it's it's dy.
You're talking here?
Yeah.
No, that's me writing the operation of taking the derivative of both sides. After I've taken the derivative, now I'm getting the dy dx.
So you don't think of it as what there is.
So if we go back and look at our chain rule, that's what's happening, right? That's why we're getting the dy dx. It's that part of it. Oops. Where are we at? We're in implicit differentiation. Come on, dum-dum. Okay. Now what do we need to do? Get the dy dx's onto one side, right?
How come you didn't, like, put the negative sign next to just make it negative y squared?
I just was trying to go not simplifying until I needed to simplify so I didn't confuse anybody when I was doing stuff, to be honest with you. Not that you would have been like necessarily confused, but I feel like somebody would have asked that question. So I factor out the dy dx, and then I'll divide both sides by cosine xy minus cosine x. It's okay. It's just the greatest common factor. So like this guy pulls to the front. Oh, I forgot the 2y. That's why you're confused.
Why would have it the other y, not the x plus y? Fix it. Oh.
Does that feel okay? Now, if I'm looking at this, I doubt this is going to be how they're writing in the back of the book. Notice how both the terms in the numerator are negative. I suspect that they'd multiply the top and bottom by a negative. And then write it this way.
With the square on the side.
That's a mistake. Thank you.
This way is right, though, right?
Yeah, it's not incorrect. I'm just saying, like, if you looked in the back of the book, I doubt that's the way they'd write it, but. So far, so good? Okay, that one's done. No, so what are we asking for here?
That second gives us a.
Oh, the second.
That's the way you write it.
What was that double five?
Mm-hmm. So doing a second derivative. Okay, so let's see how this works. We're starting by just doing a first derivative. So derivative of 4x squared is, I'm sorry, for x squared. Thank you. And then plus. Yeah, thank you. Jacob's the only one here that's consistently given me that part. That's okay. And then that equals
0.
Okay.
Wait, so you only, just for now, we're just doing the first derivative?
You can't go straight to the second.
Okay.
Now we have some options here. Okay. I can get the dy dx by itself and then differentiating both sides. What are you going to notice we'd have to do if we did that, though? You're going to have a quotient rule involved.
Yeah, so, oh, it's what? But like, it would be there, like.
I do the same thing.
Okay. So if we got the dy dx by itself, we'd have to do a quotient rule. Fine. Maybe not great, but fine. Or, what if I just took the derivative of both sides again the way it is?
Does that count as a second?
Oh, that's a lot easier.
So let's do that. What's the derivative of 4x cubed?
12x squared.
How do I do the derivative of 4y cubed times dy dx? I gave you a hint there.
Product.
Product rule,
Yay.
right? Remember when I said times dy dx? So we're going to have 4y cubed times the derivative of dy dx plus dy dx times the derivative of 4y cubed. Okay. And this still equals 0. What's the derivative of dy dx going to be?
D squared y.
D squared y dx squared. What is the derivative of 4y cubed? 12y squared dy dx. Everybody's okay? The derivative of dy dx is d squared y dx squared.
Let's just say the derivative.
That's the symbol we use to say take the derivative of it. Right? It's like putting the square root, like d dx of x is equal to 1, right? That's like saying square root 4 is equal to 2, where like this is the symbol to tells you take the derivative. This is like the argument, and then this would be like the result, right? Does that feel okay? Okay, so the d dx is just the name, the symbol we use for the operation of take the derivative. Okay? We did, but we had to use the chain rule, or I'm sorry, the product rule to do that. So again, if this is like f and g, this is like f g prime f, right? Is that okay? All right. Let's go and get the d squared y dx squared by itself. So far, so good. Well, I had 1 dy dx times 2 dy dx's. Hold on, we're not done though. Oh, the 4 should be gone, sorry. Thank you. Yes.
Is that still y cubed on the bottom, or is that?
Yes, that's still y cubed. Yep, that's just Mr. Kulik's messy penmanship. What more do I still need to do to this though?
That
dy over dx. What is that equal to?
y prime.
Right? So now I'm going to plug that in.
And you got your first derivative.
I just took it from my first derivative and got the dy dx by itself. In hindsight, that quotient rule's not looking so bad now,
Yeah.
Yeah.
Honestly.
right? Not looking so bad now.
Oh, so you just moved over the 4x cubed. That's what makes it negative, right?
Mm-hmm.
So we'll see how it works if you don't use it.
Yeah, it's most of the time it's like 6 of one, half dozen of the other. Yes.
Wait, why did we find why is the 4x cubed?
Algebra 1.
Oh, my bad.
It's okay, guys.
I didn't see it. I don't know.
Now, why did my negative sign right here go away? Excellent. Yes, because you squared it. Good. Then I'm going to just multiply the top and bottom by y to the 4th so I can get rid of the complex fraction. Actually, let's make it, it's okay. That's fine. I'm going to put the negative sign there and just make everything positive, though.
Something.
So would you have to simplify all the way down?
You need to definitely get rid of your dy dx.
Okay. That's
Like that would be, the AP would not give you full credit without substituting the value for dy dx back in. But the simplification past that, if it's a free response question, not necessary. But if it's a multiple choice, I don't know how you're going to tell without doing some level of simplification what you're at. You know what I mean?
So we'd be fine leaving that negative x cubed over 1 cubed squared.
Mm-hmm.
Okay.
Yeah, in a free response setting, yes.
Can you go back a little bit? Like, the thing in the light blue. Can you just explain that a little bit?
I'm just getting the dy dx by itself.
He's finding the first derivative.
I'm just getting this by itself, right?
Yeah, maybe we should have done the quotient row. Yeah, with the quotient row.
You should have found answer.
Oh,
Quicker.
yeah.
He said it was up here.
It's often 6 of one, half dozen of the other.
Yeah.
Like you do one way or the other, it usually doesn't matter. On occasion, it's like, oh yeah, that was a little easier to do it that way than this way, but oftentimes it doesn't really matter. Emma.
So with it's like right when you're multiplying the y because of the y4, the negative 3y squared, you just reduce it with the other y.
Yes.
To 6.
Yes.
And then once you multiply it, you just get y.
No.
And like what happened to
So this y to the fourth cancels with that y to the fourth.
But then why do you still have y to the
What?
in the end? Because you still have y to the you're gonna get it.
Well, it has to distribute here,
Um,
and then nothing happens, right? It just tacks on. When it multiplies here, they cancel. And then it has to multiply down there, and that's where the 7 comes from. This is just an efficient way of getting rid of like the fractions inside of fractions.
it goes right next to the negative 3x squared.
Yep.
Got it. I see.
All right. So
Are you almost done?
yeah, I'm gonna skip.
My brain.
I know. I'm gonna skip. I'm gonna skip these proofs for these inverse trig functions because we have 15 minutes left, and just go straight to this example. You get 6 new derivative rules here, though,
Oh, great.
for how you do the derivative of inverse sine, inverse cosine, inverse tangent, inverse cosecant, inverse secant, and inverse cotangent.
These are something we remember.
Those would be things that the expectation would be that are memorized.
Especially for an upcoming test.
Yes.
Okay.
Just memorize all of them.
Guys, we can do it. Oh, why are you so negative?
I'm not, you see all.
Does someone make a quiz? Maybe I'll make a quiz.
I should have-
Well,
actually
you
not that bad.
you say that, Elena.
No, yeah. I'll make a Quizlet.
He has a Quizlet.
You do?
He posted it.
What?
Since when?
Yeah, I even.
I told you guys. Derivative Quizlet.
You definitely told us and
Yeah, you
you
told
it
us.
right over my head.
That is
This
one day study.
quick. What's this one?
Oh,
X.
and max and minus 1.
Yeah.
Yes, knew I.
Oh. Yeah.
Oh, what do we do now? Do I press this thing? Okay,
E to the X.
good.
How? A to the X.
Nope.
X.
Oh, A to the X, LN.
LN.
Yeah.
Yeah. That's tough one.
Bro, what?
Alright,
Oh,
cool.
times G prime of X
Plus
G
Yeah.
times
It's
F
just
prime of X.
one
Yeah.
derivative.
Yes. Teamwork. Yep. Oh, G.
Top derivative.
It's product
times
rule
the
over G of X
bottom
squared.
rule
Yeah.
minus
Product
the
rule
bottom
over
top
G.
of
Instead
it.
to minus, we got it in a more efficient
Yeah, except you don't minus. I mean, you don't
Yeah,
plus.
yeah.
Oh, f
F
times g of x times g prime of x.
Do I even need this? Like.
Negative cosine of x.
No,
No,
just
positive
cosine
cosine.
x.
That one throws me.
Negative
Negative
sine x.
sine x.
Secant squared x.
Yes.
Cotangent x.
Right? Isn't this a weird one?
Negative cosecant times
I knew
cotangent.
cotangent wasn't there. That was tough. Negative.
Positive
Cotangent.
secant times
times
tangent.
cotangent. Oh, tangent.
The co's go together.
And the skis go. No. I was trying to get it.
Okay, looks like I'll be hitting.
Well, it's think about it this way. This is sine over cosine. This is 1 over cosine. So the cosines on the bottom go together.
What did you get here?
Just left in the cafe.
Cotangent.
Oh, secant squared x. No, cotangent. Oh, just tangent squared x. Cotangent.
Negative cosecant squared.
Never gonna get that.
Well, again, go back. Look, this is sine over cosine, right?
Yeah.
So you have
sine over
sine on the bottom.
Yeah. Okay. Oh. When you put it like that, it makes sense.
Tangent is secant, right? Tangent is sine over cosine. Secant squared. Cosine is the bottom.
You do.
That's the way I memorize them. Okay, sine inverse.
I didn't get to write.
We just did it.
Square root of that.
Yeah. So they're all in here, right? That's the point.
Thank you, Mr. Blue. Let's go.
And actually just the negative version of it.
All right. So let's do this example here. So it wants us to do the derivative of y equals 1 over sine inverse of x. Well, not quite, because what's going on here is a chain rule.
Yeah. Thank you.
So when we do the derivative of the outside, we get negative 1 insides to the negative 2, right? Times the derivative of the inside, right? And the derivative of sine inverse is, from the table, 1 over square root 1 minus x squared. Sure.
So how would you, so like, if you were to put some value for x squared, how would you be able to take the square root of it? Can't.
Well, think about what are the possible inputs for sine inverse. Those are numbers between negative 1 and positive 1. If I square a number between negative 1 and positive 1, it will not be bigger than 1.
So then, but you could still get 1 minus 1 then.
Yep,
Get on top.
yep.
That's okay. I mean, will you ever like have something like that then?
So if you think about it, why would the derivative of sine inverse be undefined at 1 or negative 1? Think about what the sine inverse function looks like. I see you. It looks like that, right?
Yeah.
Where this is at negative 1 and that's at positive 1. Should those derivatives exist? No. Why? Because there's not vertical tangent. It's because at that end, there's no more function. It doesn't have like a right-hand limit at the right end or a left-hand limit at the left end.
Just stop.
Because you have, yes.
Okay.
So that makes sense to me. Elena. Yes. Emma.
How did we get the negative 2 off the second one?
This negative 2 up here,
Yes.
I subtracted 1 from the exponent when I did the derivative for the power rule.
Oh.
Is that good? All right. And then B was x times arctangent of square root x. What the heck is arctangent? Same as tan inverse. Good. So what do we need to do the derivative of this?
Oh, hi.
There you go, thank you. So x times the derivative of tan inverse of square root x plus tan inverse square root x times the derivative of x. How do I do the derivative of tan inverse of the square root of x? Chain rule, very good. So the derivative of the outside is 1 over 1 plus x squared, but the x in this case is actually square root x, right? And then we have times the derivative of the inside. Is everybody okay there? Then we have tan inverse of x times derivative of x, which is just 1. How do I do the derivative of square root x?
X, or
1/2 x to the negative 1/2. I thought so. And then if I combine my like terms here, what's x times x to the negative half? X to the positive 1/2. So I'll just write that as square root x on top. That's probably the way they would write the answer. Feel okay? Yeah. Again, this gets like very algebra-y. Like there's a lot to keep track of when we're doing some of these implicit differentiations or when you have to do some of these inverse trig rules, right? Because these inverses, the derivative is a little bit more complicated. It's okay. Where's my assignment here?
Oh, woo!
No,
Yes.
You guys are crazy.
Crazy happy about to know homework.
You crazy like a fox. Yeah, let's see here.
You got it good. Did we have a homework list today?
No, because we didn't.
we didn't do anything.
We just answered questions last time.
Yes.
Wait, is this due this Sunday? What do we do next Sunday?
Next Sunday.
Next Sunday, because we wouldn't have a chance to take any questions. I never try to assign something before you've had a chance to ask questions.
What?
Tell them that you're kicking my chair and I'm going over here and keep like moving my feet. No, you actually just kick my chair. Over and over. Have issues.
These guys are actually What? No.
No, he's ready.
You
guys have practice
I can see all my I can see going
You know, I'm so happy.
Oh, yeah.
Yeah, so I start at 4, we should get half time, by like 5 minutes.
Oh, wait.
I have to swim at midnight.
I'm gonna be there.
Yeah, it's the same with us,
Oh.
but.
And I just don't, I didn't understand the MCQ.
Like I made it. I made it right now. That's true.
Okay, I totally got
Like
it.
sleep at home.
Nothing could be worse than what I said for that one question on religion. Like, I just, wow.
Get out.
I don't think I'll ever. I was
I mean, no, I'm up for sure.
Thank you.
I'm 65 right now.
It's fine, I still got
I mean,
The frown face on my paper that he made.
but you know, but
Like, he did not like this page.
is, I take it.
Silly.
Oh my gosh, I still remember when you did that one of my trade tests. I was like,
Stressing.
Which I already did for this fellow. How'd you do?
He did not like this page.
I'll go over this later. Oh, wait, I did get one totally right.
Oh, I got that one right.
Let's go with it, bullet.
Oh, of course I got this paper wrong. What's the answer to number 8?
Hey.
I was gonna say number 5, one person between the two sections did number 5 correct. Yep, number 5 on the free response, one person from both sections did that completely correct.
Ooh.
Woo. Yes, Rita. Thanks, guys. Yay,
So-
Rita.
Almost no one, or Rita was the only one that recognized that there was a product rule inside of that quotient rule.
Oh, Rita.
So good on you.
Did I just not circle anything for number 3? Wait, number 5 on 3.
Oh, so I just didn't like these.
I like found
Dude, I did the
Oh,
I didn't do the exposure rule.
Part 2.
I'm an idiot. I didn't run into denominator.
That's what I was talking about.
I got a 2.5 out
I
of
agree on that
3.
exact same frowning face.
You didn't do the product
Exactly
rule.
right there. So I didn't-
You know the derivatives, right?
What did I do?
In all honesty,
What did I
I'm
do?
gonna over this.
I was like halfway there.
You were most of the way there.
Yeah.
Oh, no, I was like
Dying to that whole test.
What? Like, I don't like my face. All the red marks. What do you want? I still can't hear you. You're like talking downward. You said. But I remember, like, for the first one, I remember a lot of it from the MCQs that we did.
Yeah, the
And I
MCQs
like
that we
studied
did
so many of
helped
those
me, like,
that I got like a good amount right.
Yeah, lots of reports.
Yeah.
I give you 60 of them.
Yeah.
Only fair that put some in there.
For this, can I just literally forget to put it?
No, because I was looking at the multiple choice that helped me out so.
Yeah, and I couldn't tell if this was scribbled out or not. So I felt like that was.
I did, I thought it would have been wrong anyway.
Right, yeah.
So I just forgot to
Yeah,
ask.
you were close. I saw you doing it over here. I was like, yes. And you got down here. I was like, what?
Sometimes I do it like that way, and then I just don't know the algebra that I need to do, and I try and do it a different way.
I was like, ooh, good, he's doing it. And it's like, oh no, he screwed some algebra up.
Hi, Mr. Bullock. Have a good weekend. Have a nice weekend.
Bye. You too. Good luck tonight.
Rita's such a smarty pants. I wish I had her teeth.
You're wearing sweatpants. What the heck is she talking about? Huh? You're wearing sweatpants. What is she talking about?
Good one, good one.
That was a good one. It took me a second.
Nailed it.
I like that
I was
one.
like, what is she talking about?
Wait, wasn't I supposed to, right? Or wait.
So
Rita's getting nitpicky about
cosine of 1 or cosine of 2.
Rita, did you get like actually 100?
She got 117.
Oh, wait.
But like cosine of 2
No.
times pi
I
over
didn't do that. I got 3 multiple choice wrong and 2
2
points off on
Yeah.
that.
So I got 6 multiple choice wrong.
Still got 100.
Yeah, I'm not
Mr.
exactly
Cool,
sure.
do you want to be a character in my creative nonfiction memoir.
Oh.
Or creative fiction memoir. Do you want to know the premise of it though?
No, you finish it and surprise me, and then you can tell me like what I end up doing in this fictional memoir.
Okay, because it won't be ready until like Christmas break though. It's our final.
Yeah, that's okay.
Alright.
I'm a patient man.
I got
I can wait.
You are very patient.
That's a good one.
You just like have to go home and just.
Not the cake I'm gonna have.
I don't know what happened. Wait to sign out. Don't ask the person next to you because the name is said. And I keep going because I don't know that you're asking questions. Yeah, you just stop me and ask. Be like, wait, hold on. I think it'll be better for everyone.
Okay, 4. Short answer. Yeah, 4. Are we doing anything for bowling today?
I don't think so.
So are we able to bowl something instead today?
I prefer that no bullying happens today.
No bowling summer.
You got